living through a strange and uncertain time. The pandemic has kept me away from the laboratory for almost 2 months now. Prior to that, you could say that I enjoyed a pretty good balance in favor of experimental science rather than theorizing about consciousness and cognition. This podcast was born as the lockdown took hold, and it has allowed me to stay engaged in neuroscience even while I'm not implanting rats with neural probes or watching local field potentials dance across the monitor. But some pretty legendary science has occurred in the realms of observation and theory. Charles Darwin seems to have arrived at his theory of evolution by means of natural selection in a post hoc fashion. Having traveled aboard the HMS Beagle, collecting detailed notes and observations about nature, he went home to England and came to develop what we now regard as the greatest insight in the history of biology. Darwin wasn't conducting experiments to test hypotheses. He was engaged in theoretical science. The data that are now available in the neuroscientific literature are vast, and I believe whole careers could easily be built upon puzzling the connections among them without ever drawing a solution through a pipette or probing rodents with electronic devices. All the literature will continue to expand as armies of hardworking graduate students and postdocs apply newer and more refined techniques to a myriad of interesting hypotheses. When this lockdown ends, I'll be among them. What determines whether a particular stimulus impinging upon the receptor systems of the body will result in a conscious percept? What must take place for a thought to burble up from the unconscious? In other words, what is the threshold of activity that must be reached for the conscious mind to become aware of something? Clearly, there must be a bottom-up saliency effect that determines whether or not a stimulus is sufficient to make a conscious impact, to produce conscious content. Consider the hairs on your skin, for example. Tiny movements and air currents certainly produce effects in the receptors upon the skin. These result in action potentials that shoot up the spinal cord, arriving in the brain and stimulating the appropriate area of the somatosensory cortex about 20 or 30 milliseconds later. But I don't need to convince you that the vast majority of these never produce awareness. Conscious experience is limited. Given a more robust stimulus, these effects are expected to be quite conscious. This is true for visual stimuli too. A simple masking experiment carried out by Kalanit Grill-Spector showed that subjects shown a flashed picture on a screen followed by a scrambled image could clearly detect those images that were flashed for greater than 100 milliseconds, but it became difficult to detect below that. She used fMRI to scan the visual cortex of her subjects and found that the primary visual cortex V1 showed activity regardless of the masking. By contrast, in higher visual areas of the cortex, like the fusiform gyrus, the subject's report of whether or not they detected the image was nicely correlated with amplified brain activation. Stanislas Dehaene describes similar experiments that he carried out in his book Consciousness in the Brain, in which he says, quote, "By measuring the amplitude of this activity, we discovered that the amplification factor, which distinguishes conscious from unconscious processing, varies across the successive regions of the visual input pathway. At the first cortical stage, the primary visual cortex, the activation evoked by an unseen flashed word is strong enough to be easily detectable. However, as it progresses forward into the cortex, masking makes it lose strength. Subliminal perception can thus be compared to a surf wave that looms large on the horizon but merely licks your feet when it reaches the shore. By comparison, conscious perception is a tsunami, or perhaps an avalanche is a better metaphor, because conscious activation seems to pick up strength as it progresses, much as a minuscule snowball gathers snow and ultimately triggers a landslide." Unquote. In those experiments, Dehaene compared words that were flashed before subjects subliminally by masking to those words flashed and seen consciously. He found that masked words activated cortical networks specialized in reading words, but visible words activated those networks much more. Furthermore, with the visible words, he reported amplified activity that spread to parietal and prefrontal cortex as well. So consciously seen images have higher amplitude activities, and those activities spread widely in the cerebral cortex. Dehaene conducted these experiments with sounds, too. He saw the same thing as with the visual system. With subjects situated inside of the fMRI machine, he presented sound pulses through headphones, at a volume so that subjects consciously hear them about half the time. If the sound was not heard by the subject, the researchers saw activation of the auditory cortex anyway. But when the sound was actually heard, the amplitude of activation was higher, and the activation in the auditory cortex was accompanied by activation in the parietal and prefrontal cortices. I told you previously about the study by Dan Simons and Christopher Chabris, in which viewers were asked to watch a short film showing two teams, one in white, the other in black, tossing a basketball. Viewers were told to count the number of passes made by the team in white. In the middle of the film, a man in a gorilla suit enters, he beats his chest for a few times and then he leaves. In this task, the majority of subjects never saw the gorilla. Cognitive studies like this one reveal the limitation imposed upon consciousness by attention. Attentional blink is a similar phenomenon. This occurs when a subject is briefly distracted and so fails to perceive a visual stimulus that occurs right before their eyes. Incidentally, this is how magicians accomplish their sleight of hand. Dehaene and his colleague, Claire Sargent, exploited attentional blink in an experiment designed to determine the amount of time it takes for the widespread activation to occur following a conscious visual stimulus. They used EEG to simultaneously record activity in the visual cortex and the prefrontal cortex. Words were flashed to the subjects at the moment when they were distracted by a different visual task. So on some trials, the subjects would perceive the words, and on other trials, they wouldn't. Dehaene and his colleague could compare the EEG results between unseen words and visible ones. For about the first 200 milliseconds, the EEGs looked the same, with activation of the visual cortex. That's pretty much the end of it for trials in which the word was not perceived consciously. But for those trials in which the word was seen, the activity became amplified between 200 and 300 milliseconds and then spread to associative cortical areas and the prefrontal cortex. Dehaene refers to this wave of activity as global ignition. This wave appears to function as a threshold response for conscious perception. If some threshold of activation is met, then a global ignition event will occur, and an appropriate conscious content will appear. In episode 5, I told you about work by Marcello Massimini and his colleagues. In human subjects, either awake or in different sleep states, they use transcranial magnetic stimulation to induce activity in some area of the cerebral cortex and record EEG from areas spread across the cortex. I'll read to you again what Massimini and Tononi wrote in their book, Sizing Up Consciousness. Quote, "When everything was ready, we asked the student to stay awake, and using neuronavigation, we targeted the TMS probe and set it to the right intensity to activate cortical neurons. We turned on the stimulator, which started pinging the cortex regularly, once every 2 seconds or so, and we took our place in front of the monitor to appreciate the brain's electrical echo. The first measurement met our expectations. The initial activity, triggered by the magnetic perturbation in the site immediately below the stimulator, shifted from one cortical area to another, reverberating for approximately 300 milliseconds. The end result was a complex chain of causal interactions in which many areas distributed across the cortex lit up and shut down in different ways and at different times. We declared ourselves satisfied. We had knocked on the waking brain and had recorded the distant echo of diversity and unity. Then we turned off the lights and told the student to try to catch some sleep. After about 20 minutes, we were ready to probe for the first time a brain caught in the large waves of deep, non-REM sleep. We switched on the TMS again and aimed it at the coordinates of the same group of neurons that we'd stimulated before, releasing the exact same magnetic field. We stared at the computer monitor glooming in the dark, and after a few pulses of TMS, the response of the sleeping brain was already clearly visible. The area just below the stimulator bounced with a positive-negative wave of electrical activity, which was obviously larger than the response recorded in wakefulness. However, the electrical symphony had gone. It was almost as if the coarse physical composition of the brain had changed. The multiform echo that resounded through the entire cranium had given way to a dull thud. The initial response was large, but did not propagate beyond the area that was being directly stimulated, and the cerebral cortex seemed fragmented. We shook the student awake and asked him what he was feeling, what he remembered of what was going on in his mind. The response? A laconic nothing, as if he had not been there." Unquote. Under anesthesia, they saw the same result as in non-REM sleep, and in REM sleep, the result was the same as during wakefulness. This extends what Dehaene saw with regard to global ignition. It looks like conscious contents occur in correlation with this global ignition, and these global ignitions do not take place during states of non-consciousness. So what is happening in the cortex on the way toward reaching the threshold for conscious contents? I think the wave of activity reported by Dehaene when words were consciously perceived by his subjects is the spread of integrated causality. A few neuronal elements are firing action potentials that stimulate other neuronal elements to fire, and so on. Each link in this spreading network of activity requires time for signal transmission, synaptic transmitter release, and reception. The stimulus will not result in conscious content until and unless a subsystem is formed. As I have said many times before in reference to the temporally integrated causality landscape, that subsystem must have a level of temporally integrated causality that exceeds that of the larger integrated thalamocortical system in which it exists. Some critical number of action potentials will need to be exchanged before the subsystem emerges and is distinguishable from the background noise. Benjamin Libet conducted stimulus experiments using electrodes targeted directly to the somatosensory cortex in patients while they were awake. Of course, the sensation that occurs with these stimulations occurs in some area of the body, not in the brain. In his book Mind Time, Libet wrote, quote, "The stimulus consisted of brief pulses of current, each about 0.1 to 0.5 milliseconds duration, in different experiments, repeated at 20 to 60 pulses per second. A time factor turned out to be the most interesting requirement for eliciting a conscious sensation. To elicit a report of a weak, threshold-level sensation, the repetitive stimulus pulses had to continue for about 0.5 seconds. That requirement was surprisingly long for a neural function. How was this measured? With a long 5-second train of those pulses, the intensity had to be raised to some minimal level in order to produce the weakest conscious sensation. When this liminal intensity train of pulses was shortened below 5 seconds, the duration of the conscious sensation, as reported by the subject, was also shortened. But the perceived strength of the sensation was not changed. Finally, when the liminal stimulus train was shortened to below 0.5 seconds, the sensation vanished." Unquote. This suggests that there is a durational threshold in the cortex. A stimulus on the skin or a visual stimulus has to achieve a sufficient level and duration of activity in the cortex to become conscious, and conscious contents only appear when this has been met. Stanislas Dehaene, elaborating on the theory proposed originally by Bernard Bars, has been a proponent of the global neuronal workspace model, GNW, which I have talked about previously. The threshold for consciousness is consistent with GNW. In a recent review on the model, George Mashour et al. Write, quote, "It is important to note that the GNW hypothesis is not a localizationist approach to conscious access, nor is conscious access posited to exist solely in a given node of the GNW. Rather, the GNW acts as a distributed router associated with millions of neurons distributed in many brain regions through which information can be amplified, sustained, and made available to specialized sensory processors and thalamocortical loops. The prefrontal cortex is posited to play a key role in the GNW because of the greater density of neurons thought to be critical for global broadcasting of information, but it is not proposed as the exclusive territory for conscious access. The GNW was indeed initially suggested to include the dorsolateral prefrontal and inferior parietal cortex together with a set of specialized and modular perceptual, motor, memory, evaluative, and attentional processors. Other cortical hubs, such as the anterior temporal cortex, anterior and posterior cingulate cortex, and precuneus, may be equally important. Note that these areas are neither identical nor redundant. Each has their own functional specificity and connectivity pattern, yet the communication between them is so extensive and rapid that any information available to one is quickly made available to the others. Their tight bidirectional connectivity creates the conditions for ignition, i.e., the triggering of a sudden collective and reverberant coordinated activity that mediates global broadcasting." Unquote. I propose that the threshold for conscious perception of a stimulus is identical to the threshold for producing a subsystem. That is to say that some set of neuronal elements must achieve a level of temporally integrated causality that is higher than that of the whole system. As soon as they do, a conscious content will appear from the point of view of the system. What that content is like depends upon which parts of the system are involved, their precise geometry within that system. I think that the data are consistent with this framework, and while it has its differences from GNW, there are areas of agreement. In Libet's experiment, the conscious content was sustained while the stimulus was sustained. According to the TICL framework, as long as the subsystem is maintained, the content will persist in consciousness. The subsystem is also capable of change. It could come to include new neuronal elements or to drop others. This would result in a change in the qualitative experience of that content in consciousness. Suppose you are watching a rabbit wander across an area of lawn. The rabbit stops and sniffs about, then takes a few hops. The area of the retina upon which the different features of the rabbit fall, the angle at which it is seen, the position of its ears, etc., will all be shifting about as you observe what it does. These movements and changes cannot result in new stimuli because, as Libet has revealed, that would require a new 500 millisecond waiting period to occur before the new stimulus would become conscious. But instead, you track the animal continuously, and it persists in being in your conscious composition. The subsystem or subsystems corresponding to the rabbit remain present, but they may undergo change, particularly with regard to the cortical map regarding its position on the lawn relative to other objects on the lawn. This reminds me of something which goes wrong in the case of visual anosia for motion or in cinematographic vision disturbances in migraine. Oliver Sacks has described such conditions. In his book, The River of Consciousness, Sacks writes, quote, "There is a rare but dramatic neurological disturbance that a number of my patients have experienced during attacks of migraine, when they may lose the sense of visual continuity and motion, and instead see a flickering series of stills." With regard to motion blindness, he wrote, quote, "A woman who, following a stroke, became permanently unable to perceive motion. The stroke had damaged highly specific areas of the visual cortex, which physiologists have shown in experimental animals to be crucial for motion perception," unquote. He describes that the patient saw instead a series of freeze frames lasting several seconds. It's highly speculative, but I can imagine that neurons in the visual motor areas could be part of the subsystem necessary for its maintenance, as other neurons in the mapped visual cortex are dropping out of the subsystem and being replaced. With watching the rabbit, it has changed its position in space. Imagine if the subsystem had to be reconstructed every time such a change occurred, and not just the rabbit, but everything in vision. This could lead to something like a freeze frame effect, because the new stimuli, starting from scratch, as it were, would have a lag of half a second or more before they could become conscious contents again. As I said, this is highly speculative. At the University of Michigan and around the world, the pandemic has sent university students home in the middle of an ongoing semester. Students have been conducting their studies remotely and connecting to their professors via the internet. It has occurred to me for some time that the university model of higher education might be radically changed with the ubiquity of information technology in which we now live. I wonder if the novel coronavirus has given a jump start to that change. And if so, I wonder what it could mean for academics like myself at this transitional time in our careers. I envision an office in some brick-built structure, with bookshelves cluttered and a window overlooking old-growth trees and well-worn paths ranging between them. But, to my inevitable disappointment, I think that is a 20th century vision of what it means to be an academic that might soon be overtaken by the realities of the 21st.